this lecture, we'll discuss two very popular types of probability. They're popular because they are very useful. The two types are the binomial probability and the normal probability. First, we'll look at binomial, and in the latter half of this lecture, we'll talk about the normal probability distribution. There are three requirements for a distribution to be binomial, and those requirements include the fact that there must only be two outcomes. And when you start talking about situations with only two outcomes, you begin to talk about a Bernoulli population. The name coming from Jacob Bernoulli, who worked very much in the area of binomial probability. Here we see a picture of two of the Bernoullis. It was a very prodigious family in terms of mathematics and science, enjoying a quiet night at home. Since they had no TV and had no stereo, they were working math problems at the chalkboard. Notice how they're dressed formally, because you didn't want to be dressed informally to do mathematics problems. But Jacob Bernoulli lent his family name to a type of probability distribution. The two outcomes that in a Bernoulli process would be a success and a failure. Now, no emotion should be attached to these two names. For example I like to give, if you're a geneticist and you're looking at the results of fruit fly egg hatchings, would a blue-eye fruit fly or a green-eyed fruit fly be a success? I'm not sure, but you label one a success and the other must be a failure. There are only two outcomes. The second requirement is that each event in a trial is independent. That is, that what happens in one event does not affect the result or the probability of the next event. And therefore, if you have a situation where something is changing, and if it's sunny today, it affects the probability of it being sunny tomorrow, those are not independent events. That would not be a Bernoulli population, and it could not be a binomial probability distribution. The third requirement, which is not specific for Bernoulli, but is for binomial, is that there is a fixed number of events. In a Bernoulli situation, as we'll see later on, you could have events that go on until something happens. So in a binomial situation, we have these two outcomes, success and failure, and their probabilities are given a specific label. The probability of success is equal to lowercase p. The probability of failure is symbolized by lowercase q, and of course q equals 1 minus p. Using terminology from the previous lecture, Q is the complement of P. Now, once again reviewing, we're talking about a binomial distribution. There must be all three things at hand. First, two outcomes. Second, the outcomes must be independent. The probability does not change from event to event. And the third is a fixed number of simple events, a fixed number of events in a trial. There are many situations that are binomial in nature, and we're going to look at a few of those. And again, at the end of the trial, what we're concerned about in these binomial situations is the number of successes. How many wins, how many sales, how many green-eyed fruit flies. Genetics, as I mentioned already, is an area where concern about the dominant and recessive genes offers many opportunities for the use of the binomial distribution. The world of sports is full of binomial situations. Win-lose, ball-strike, score, do not score, make the shot, miss the shot, penalty, no penalty, are all binomial situations. In medicine, it's obvious that the outcomes of surgery or other medical treatments are binomial situations, because either you have a success, which could be a cure, or a failure, lack of cure. Politics, being a win-lose situation, has many situations that are binomial. Businesses faced with decisions about products, personnel, and strategies must use binomial outcomes to aid in decision-making processes about those types of decisions. In our personal lives, we are faced with success-failure decisions about marriage, vacation, employment, relocation, and many other opportunities to use a binomial situation if you understand the mathematics and can use that mathematics to help you make a decision. What is the chance of success? The binomial probability formula can be determined after observing a simple binomial situation. We have a 3-question multiple choice test where each question has a choice of 4 answers. Only one of those 4 answers is correct for each question, and the person taking the test is pure guessing. That is, he or she has no idea what the correct answer. Perhaps the questions are written in a language that he or she doesn't understand. They're going to just guess A, B, C, or D for each of the questions. Now, since the test has 3 questions, n equals 3. And the probabilities for success, getting the question right, and failure, getting the question wrong, must be P, 0.25, and Q of 0.75. Because obviously, if you have 4 choices and only one is right and you're guessing, you have a 1 chance in 4 chance of predicting or picking the right answer. So we determine the probability of a specific number of correct answers. We'll use a chart. And here's the chart, and we can see that X is the number of successes. The number sign represents the number of ways to get that kind of result. And then we have the probability of getting X successes. And obviously, if we have 3 questions, each question being an event, then the number of failures must be equal to 3 minus X. And therefore, the last column shows the probability of 3 minus X failures. The first row shows the result for 0 successes. A person takes this 3-question test and misses all 3 questions. Well, there's only one way to do that: get all 3 questions wrong. And to do that, the probability of getting 0 successes is irrelevant. We're really concerned about those 3 minus 0, that is the probability of getting 3 failures, which is 0.75 times 0.75 times 0.75. Okay. Now, the probability of getting 1 success, answering 1 question correctly. There are 3 different ways to do that. And we discussed the reason for that in an earlier lecture on Pascal's triangle. The probability of getting 1 right is 0.25. The probability of getting 2 wrong is 0.75 times 0.75. And we multiply in those cases because, you see, those events are all independent. And the probability of getting 2 right, there are 3 ways to do that. The probability of getting 2 right, 0.25 times 0.25, and the probability of getting that 1 question wrong is 0.75. To get 3 questions right, there's only one way to do it: answer all 3 questions correctly. And therefore, the probability must be 0.25 times 0.25 times 0.25. The number of outcomes leading to a particular result is symbolized using NCX. The C stands for combination. The N is how many events you have in the trial. The X stands for the number of successes. These, the values for NCX, by the way, are found in Pascal's triangle, as we'll soon see. Based on our problem, the binomial probability formula is shown as P of X equals NCX, that is the number of ways to get a particular outcome, P to the X, which is the probability of success raised to the X power, X being the number of successes, times Q to the N minus X power. And again, Q is the probability of failure, N minus X is the number of failures if you have X successes in N events. Blaise Pascal, of course, discovered the way to get the values for the number of ways to get a certain outcome, that is the NCX. And actually, he published this information in 1665. I shouldn't say he published it. It was published because this was 3 years after his demise. And again, we mentioned this before, but I really want to mention this again, that although the triangle is named for him, he did not discover it. He discovered uses for it. It was known to Omar Khayyam in 1100. It was known to the Chinese in 1303. But let's take a look once again at Pascal's triangle. And this should be familiar to us. We've seen this in a previous look at patterns in the whole numbers. And if you write Pascal's triangle as a right triangle, it becomes a lot more helpful in terms of binomial probability. So here is a chart, and you'll notice in the upper left-hand corner it has n/x. And what that means is that the column under that has the values of n, 0 through 6. Obviously, you can extend this as far as you'd like. The row to the right of n/x has the numbers 0 through 6, which is the x, the number of successes. So if I wanted to find out the number of ways to get 4 successes if I have 6 events in a trial, I would say, well, let's see, I have 6 events, that's n is 6, and an x, the number of successes, is 4. If I go down to I see 6 in the left-hand column and go across until I'm under the 4, the number in that column, in that location, is 15. That means that NCX, or the number of ways to get that outcome, 4 successes in 6 trials, is 15. There are 15 different ways, which means, another way to look at that is if you had 6 people and you were going to select 4 of those people to go on a trip with you or ride in your car, there would be 15 different groups of 4 people that you could select from those 6 folks. Now, obviously, many of the groups would have similar people in them, but there'll always be someone who is different. 15 different ways to do that. And, of course, you remember that Pascal's triangle gets quite big. The numbers get quite big as you go down. So as we increase the number of events in our trial, the number for NCX becomes fairly large. And, again, this can be done on a calculator or a computer. Now, the binomial probability, we have a formula, so it's easy to come up with the probability. It's easy to identify an event that is a binomial situation. We'll talk about normal shortly. And therefore, it's a very commonly used probability distribution. Because what happens is that once we see, for example, let's say we were looking at a sales situation, and we knew that we set one of our salespeople out to make calls on customers. Let's say in the pharmaceutical business, where the salesperson was calling on doctors. And at the end of the sales call, the salesperson would indicate whether or not that doctor had agreed to, let's say, distribute free samples of a new drug the pharmaceutical company was manufacturing. So we have success and failure. And based on past performance, we come up with a probability of success, and 1 minus that would be the probability of failure. We would assume that as the salesperson went from doctor to doctor, the probability didn't change, so they were independent. And we'd assume that the salesperson would see a fixed number of doctors each day. And that would be, therefore, a binomial situation. Well, now, using the binomial formula, we could easily obtain expectations as to the probability of that salesperson having 0 successes, 1 success, 2 successes, etc., through the day. And, of course, multiplying by the number of salespeople and the number of days the salespeople are traveling about to doctors, we can begin to make sales forecasts and production forecasts to get those free samples manufactured in enough quantity to be able to distribute to the doctors so they could give it to those patients. So the use of binomial probability would quickly help us make some important business decisions. Let's now take a look at normal probability. And normal probability is called normal because it is. It happens a great deal of the time. Many, many situations are normal. The normal distribution is represented by a specific exponential function, and work on this function has been going on for nearly 300 years. The normal probability distribution is defined by the exponential function shown here. P of x equals 1 over sigma, that's the written Greek letter sigma, times the square root of 2 pi, e to the negative 0.5 times quantity, x minus mu over sigma squared. Looking at that formula, it appears to have quite a few Greek letters. Let's explain what those letters stand for. The sigma is the population standard deviation of a distribution. The pi we already know about. That is the 3.14, etc. The e, of course, is that exponential natural base. X would be the measurement we're concerned about. Mu would be the average, the population mean of all the measurements in the population. And once again, we have sigma. So basically, this is a distribution that tells us if we're a certain measurement away from the mean and using a known standard deviation, a measurement of variance, a variation that we will talk about in detail in a later lecture on data analysis, that we can come up with a probability based on this exponential function. The earliest analysis of the exponential function, of this particular function, was done by Abraham de Moivre, a gentleman that we've come to know in other areas. And de Moivre published a book in 1718 called The Doctrine of Chance. In reality, this was a book about probability. And he was discussing in that book the normal probability distribution. Carl Gauss, a name, again, we've mentioned, a German mathematician who is well known as a very brilliant man, extended the work of de Moivre at the beginning of the 19th century. Because of his work in the area of the normal distribution, normal probability, the normal distribution is often referred to as the Gaussian distribution for Gauss. By the way, it's a little side note on Gauss. He is, again, a story that is told, and we assume it's true, that he was a very young man. He was quite precocious, especially mathematically. And in the typical classroom at the time, the instructor was very upset that Gauss always had the answers and would interrupt his lecture with answers to questions that were not yet even asked. So one day, he told young Carl Friedrich to go in a corner and add up all the numbers from 1 to 100, thinking that this would take the young man a few moments, and at least he would have that time to work with the rest of the class. Gauss put his head down, looked up, and said 5,050. The instructor was flabbergasted. He said, "How'd you know that? Did you memorize?" "No." And very quickly, Gauss explained to this mathematics instructor how he had done it, and which led the way to something called arithmetic progressions. And Gauss was probably maybe 6 or 7 or 8 years old at the time. Whether the story is true, we don't know, but it's kind of nice to know there are students like that out there. I'm waiting to have a few. Anyway, so we have Gauss working on the normal distribution. And the normal distribution is a continuous function. That is, any value of x is possible. We can find a probability for any value of x. And we use integral calculus to find area under this exponential curve. Since the distribution is continuous, the only type of probability that can be found is a probability of result being greater than x, some value, less than x, or possibly between two values of x. Theoretically, the probability of a specific individual numerical value is 0. That is, the probability of your being exactly 6 feet tall is 0. You are between 5'11.99" and 6'0.00001. Because indeed, how do we measure your height? There's error involved, and we can get into a great deal of theory, but suffice it to say, in a continuous distribution such as the normal, we can only talk about the probabilities in an interval. Less than a certain number, greater than a certain number, or between two numbers. Many uses of the normal distribution are for distributions that are not continuous, but that are discrete. And we make adjustments that are easily made to use the normal distribution even for a situation that is not continuous, where there are only specific answers possible. All normal distributions are symmetric. And they're symmetric about the mean, that is mu, no matter what the mean and standard deviation are. The mean, the median, and the mode, 3 types of averages that we'll again discuss when we talk about data analysis, are all the same in a normal distribution. For any normal distribution, the probability of being in an interval from 1 standard deviation below the mean to 1 standard deviation above the mean is always about 68%. The probability of being 2 standard deviations either side of the mean in that interval for any normal distribution is approximately 95%. And the chance of your being within 3 standard deviations either side of the mean, mu, is 99.7%. And this is true for any normal distribution. This is called the 68, 95, 99.7 rule. Sounds more like a football play, but it's quite significant because it allows us to know For example, if we know mu, we know sigma, and we have something that's normally distributed, the probability of being within one standard deviation is about 2/3. Quite significant. This is used especially in areas of IQ. Without getting into it, specific intervals in the normal distribution of IQs are given names based on the number of standard deviations. For example, you can belong to an organization such as Mensa if your IQ is 2 standard deviations above the mean IQ for all folks. In school situations, a student will be considered in need of special help as learning disabled if he or she has an IQ that's closer than 2 standard deviations below the mean, and still has indicated through his or her achievement that they are not up to grade level. And there's specific examples, but the fact is that 2 standard deviation notion, I should say it's a 1 standard deviation notion, is quite important. And in some cases, the 2 standard deviation notion would cut off a person from being given help because they would be considered educationally handicapped. But anyway, the point is that IQ, which is something we all know about, but very few people know their own IQs, the whole idea of IQ and looking at classifications is based on that 68, 95, 99.7 situation. Okay. The central limit theorem, the CLT, is a very important theorem in terms of the use of the normal distribution. The CLT was first worked upon by Simon Laplace, another one of the great French mathematicians, and this is used if the population's standard deviation, sigma, is known, and if the sample is large enough, then we say that the distribution of all the sample statistics, and for example, all the possible sample means of all the possible samples, will be approximately normal. Distribution will become more and more normal as the sample size increases. And the CLT, the central limit theorem, is true no matter what the underlying distribution is. In other words, even if you have a distribution where the population is uniform, for example, the last digit of your telephone number is equally likely getting a 0 or a 2 or a 5. But if you start grouping people together and get the average last digit of the telephone number, it will begin to become more and more normal as the number of people in your samples increase. The standard normal table, or Z table, was developed so that only one table is required when working with a normal distribution. The value of Z is the number of standard deviations the measurement X is from the mean. That is, Z equals X minus mu over sigma. X minus mu, the difference from the mean, divided by the standard deviation, gives you your Z score. The Z table provides the probability of a measurement being less than a particular X. This is simply the area under the curve of the normal distribution for Z to the left of the Z that you computed with X minus mu over sigma. And of course, that area was found using the integral we learned about in calculus. If the probability of a measurement being greater than X is desired, we simply subtract the table value for probability from 1. The reason, because either you are less than X or you are greater than X. So therefore, the complements, we use 1 minus the probability. If X is below the mean, then X minus mu will be negative, and we'll have a negative Z score. If you're exactly at the mean, your Z is 0, because 50% of the population is below the mean and 50% is above. To find the value of X that will cut off a particular area or a particular amount of probability, one must first determine the probability to the left that you want. So for example, if you wanted the top 10%, you'd go into the table looking at a probability of 0.9000, because obviously the complement of 10%, 0.1000, is 0.90000. This would be to the left of your value. And you want to find what that value is. If we enter the Z table with that probability, 0.9000, the Z score is obtained. And once we obtain that Z score, we simply rearrange the formula Z equals X minus mu over sigma to give us the X equals mu times sigma, X equals mu plus Z times sigma. A simple example is now provided to demonstrate the use of the Z table. A particular graduate admissions test has a mean score of 600. That is, the average person taking this test scores 600, with a standard deviation, a measurement of variation, of 120. If a person scores 780 and desires to know what percentile for that score he or she is in, the z-table is used. We want to know the probability that X, anyone taking the test, their score is less than 780. Because the percentile really is a measurement of the probability of someone taking that test and getting a score less than or actually equal to yours. So we have mu equals 600, sigma equals 120, and we want the probability that X is less than 780. We need to find a Z. And we do that with 780 minus 600 over 120, which gives us a Z of 150. I should say 1.50. 1.5, 1 and 50 hundredths. And we enter the Z-table to find the probability to the left of that Z-value, to the left of 1.50. And that probability, according to our table, is 0.9332. The person who got the 780 on this test is in the 93rd percentile. There are about 7% of the people taking the test who will score higher, and about 93% who will score lower. Now, your boss, who perhaps is not on the friendliest terms with you, takes the test and receives a score of 510, much to your joy. And you really want to know at what percentile this represents. Well, we would find the z-score, and again, that would be 510 minus 600, 120. Of course, your boss would have a negative z-score. Oh, joy, the joy of mathematics. Negative 0.75. Looking at our table, the probability of being to the left below a score of 510, below a z-score of negative 0.75, is approximately 22%. So your boss is in the 22nd percentile, I guess. What about a particular graduate school that's looking to see how they should determine who is allowed to enter their program? They use this particular admissions test, and they want to only really look at applicants who are in the top 10% on this admissions test. They need to know a cutoff score. The question is, what is the minimum score to be in the top 10%? Okay, we're still going to use the z-table, but now we're going to go in with that probability. When we said the probability to the left of that z would be 0.9000, because 90% is the complement of 10%. And we go into that table, and we look at a z-score of 1.28. And with a z-score of 1.28, we use the formula, which is the other version of the z formula. We're now saying that x, the cutoff value, is equal to mu plus z times sigma. Since we know mu was 600, we know that the z is 1.28, and we know that the sigma is 120, we get a score of 753.6. So in order for a person to be considered for admission to this school, a person would have to have a score on this admissions test of 754 or higher, because that is the cutoff score. And therefore, since so many situations are normal, and as we'll see when we talk about hypothesis testing and confidence intervals in a later lecture, when we're dealing with samples and we therefore kick in the central limit theorem, everything is normal or can be approximately normal, and therefore we'll use the z-table. This table and the notion of normal probability is quite exceptionally important. We can use the normal situation for binomial situations, because it turns out that most binomial situations are normally distributed. There are certain specific requirements. If you take the number of events in a trial, in a binomial trial, n, and multiply it by p, the probability of success, and if you take n and multiply it by q, the probability of failure, both those numbers must be at least 10. If they are, then you can use the normal distribution to approximate your binomial situation. As you can see, binomial and normal situations exist all around us. Knowledge of that probability is quite important. But sometimes we don't want to compute probabilities. We'd rather have a computer do it in a way that would demonstrate effectively what's going on. Our next lecture will deal with probability and simulations, and we'll see how we do that there.